Thank you. All right. Welcome everyone to the May program meeting for the San Diego Astronomy Association. We've got a pretty cool one lined up today. We're going to talk through a couple of sort of news items, things that I've sort of collected from around the club, things that are good to talk about and I want to make sure everyone knows about. So we'll start here. One, there's been these member engagement invitations, like initiative invitations sent out to your email address that you've registered to SDAA with, the same one you would have gotten probably notification about this. These notices went out. The board has created 3 new committees, membership, events, and facilities. And these committees need people to help shape what the club does and how the club does its thing. And so I think check your emails. You should have seen some emails come through that were about these committees, and they'll have contact information there. I think mostly you can just email president@sdaa.org. Take that, Dave, and for more information. But you know, these don't have to be huge commitments. They can be pretty lightweight. We're looking for people to help. What do you want the club to be? What sort of things do you want the club to do? Let's go do them together. This is a member-driven organization, and so this is like the official invitation for people to start staffing in these committees and start planning out, what sort of cool events do we want? What sort of membership perks and what should happen at TDS? So those are the 3 big the 3 big committees. So please, or if you forget who to reach out to, you can always reach out to me. Yeah, I'll get you in touch with the board members that are running each of those committees. Also, Astro 101, the next Astro 101 is scheduled to return July 11th. This time we're doing a little bit different. We're going to have a backup date of the following weekend, as opposed to pivoting to an online one, because I think the online one was fun, but I think we all really wanted to just meet in person and hang out. As a reminder, it's a very low pressure, casual astrophotography sort of group meetup in front of Dave's house. And he's got a really big cul-de-sac and, very nice neighbors, and we can all set up there. It's for beginners to experienced members. It's for everyone. We've got really good feedback from the last couple that we've done. People are learning new things and they're meeting club members, which I think is really cool. Along those lines, another sort of thing the club is doing for us, Pad 70, which is run by Ross Salinger, is starting to produce images, really good stuff. So these 2 images you see on the screen were produced by club members using the Pad 70 scope. I think right now it's set up for people to use it in 2-week tranches. But if you want to use, basically top of the line astrophotography equipment that the club, who I think it was a generous donation, owns and operates, reach out to Ross. Or again, if you forget any of this, you can always reach out to me. And as a reminder, the next TDS public night will be Saturday, June 6th. And yeah, if you're interested in helping or if you have any questions, you can email either president@sdaa.org or you can email me. That's fine as well. Or any of the directors. I think we're any of the members of the board. We're all fairly inviting people. So just come say hi. And with that, tonight's speakers. So I should probably introduce myself. I'm sorry. I think I had these in a different order before. I'm Francisco Contreras. I'm a SDAA board director. I think I'm Director Delta. I also have a YouTube channel, do astronomy and astrophotography related things. And then we've got Jordan, who is an active SDAA member. He's going to be doing the primary presentation called A Focus on Focusing. It's going to be about, Bahtinov masks and some theory and some practical things. I'm actually really looking forward to hear him talk about it. But before we jump into that, the club, as another thing that the club does, is we sponsor some prizes within the Greater San Diego Science and Engineering Fair. These are open to people in grades 6 through 12. The 72nd fair was held just recently in March 18th, 2026. There was a committee, I think 4 or 5 club members. I think, Kin, you were one of them, right? Who went out and judged some of these and provided awards to some of the people that we thought were doing really interesting work, especially in astronomy and things of that nature. And we're lucky enough to have a couple of, at least one of the winners here tonight to give us a presentation on their science fair project and what they did, and hopefully we can all see why why this is a good thing for our club to do and continue to do moving forward. So um, with that, I'm gonna hand it off to I think it was Samuel. Are you on, Sam? Do you go by
Yeah,
Sam? Can I call
hello.
you Sam?
Yeah, yes, Sam's fine. Yeah.
Okay. Hey, Sam.
Hello.
Um,
Nice to meet everyone.
yeah, nice to meet you. So you want to just maybe tell us a little bit about yourself and then like get into your presentation? I don't. This would
Francisco, you want to
be
turn
great.
off
We're
your
excited to
sharing
hear
now?
about it.
Francisco, shut down your sharing.
Yep.
There you
Yep.
go. Yeah, well, I'm Samuel Sternson. I'm a sophomore at CCA, rising junior. And I've been interested in astronomy for a while now. This is the first like actual like science project I've done in the astronomy related space, but I've done other like science Olympiad related stuff related to astronomy and things like that. But like before this project, I was interested in stuff basically just like looking at the pretty pictures from like a lot of the cool telescopes out there. But I think this project was really interesting to me because I'd never really done anything like it before. And I think that I think it was pretty cool. So here, let me share my screen real quick. Um, so, um, so my project revolved around supernovae, and I've been interested in supernovae for a while because I think they are some of the coolest phenomena in the universe. And I'm specifically interested in mostly nucleosynthesis, which is the process by which elements are created in supernovae. And so I did some research into nucleosynthesis and supernovae, and I learned about something called the alpha process, which is where a helium nuclei would fuse with elements of low mass, so carbon mostly, and then build up as more helium nuclei fuse onto the atom to elements with larger masses, so all the way up to nickel. And so you can see here, you start with carbon, fuse on a helium, you get oxygen, fuse on another helium, you get neon, so on and so forth, all the way up to nickel. And so I learned that generally in most supernovae, light alpha elements, so around this range, are produced in greater amounts to heavy alpha elements, like over here. And we can see here in this graph of the elemental abundances of the universe that the light alpha elements over here are much more abundant than the heavy alpha elements over here. And so I actually was able to find that one pretty interesting exception to this are newly discovered and pretty rare type of supernovae called calcium-rich supernovae, which, as the name suggests, produce a lot of calcium. And so the interesting thing about calcium-rich supernovae is that they seem to skip a lot of these light alpha elements and just jump straight to the calcium. And I was pretty intrigued by this, and I wanted to find a way to learn more about them because they are relatively hard to observe. We really don't know a lot behind the mechanisms behind these supernovae and actually how they create elements in the way they do. And so like because they're hard to observe, as I said before, I wanted to find a way to indirectly observe them. And the way I thought about doing this was I realized that if a calcium-rich supernovae occurred near a star or a dust cloud that would eventually become a star, then that star would become calcium enriched. I could then find that calcium enriched star through galactic surveys and then analyze the elemental abundances of that star to learn more about the supernova that caused the calcium enrichment. And so I did a little bit more research into calcium-rich supernovae, and I found that they're theorized to be two different types, white dwarf binary and core collapse. Now, white dwarf binary calcium-rich supernovae are thought to occur when two white dwarfs in a binary system either merge or one accretes enough mass from the other to and eventually undergoes a thermonuclear explosion, while core collapse calcium-rich supernovae are thought to occur in a binary system with a massive star around 8 to 10 solar masses, and then a more sun-like type star, yeah, again in the binary system. But the shell, hydrogen shell of the massive star gets stripped away, and then it undergoes a core collapse, leaving behind a binary system. And so I thought that I might be able to find calcium-rich stars from that were enriched by calcium-rich supernovae. And I hypothesized that the that both types of calcium-rich supernovae have occurred in the Milky Way, even though only even though neither of these supernovae have actually been observed before in the Milky Way, directly at least, and that calcium-rich stars that are not part of binary systems would have low levels of heavy alpha elements, again, based on the signatures of white dwarf binary calcium-rich supernovae. And I realized I forgot to mention this, but the the white dwarf binary calcium-rich supernovae produce basically only calcium and no other heavy alpha elements, while core collapse calcium-rich supernovae produce calcium as well as some titanium and chromium and other heavy alpha elements, and they leave behind a binary system. Sorry, I should have made that clear before. And so I predicted that calcium-enriched stars that were not part of binary systems would have low levels of heavy alpha elements based on the signatures of white dwarf binary calcium-rich supernovae, and that the calcium-rich stars that were in binary systems would have some heavy alpha elements based on the signatures of core collapse calcium-rich supernovae. And so the way I tested this was by analyzing the elemental abundances from stars in the Sloan Digital Sky Survey, which is an open source database of around 733,000 stars and attributes such as their size, temperature, and most importantly, elemental abundances. And so I started with the full database. I then filtered out stars that had warning flags, which are automatically generated by the SDSS abundance pipeline. They indicate poor quality data. I then filtered for stars that were enriched in calcium, and this calcium level is based on the literature around these calcium-rich stars and calcium-enriched supernovae. And so then I was left with only one star after all of this measurements, and I went from 8 to 1 stars because I had to by eye analyze the spectra of these 8 stars that were supposedly enriched in calcium, and find any anomalies like this one. So what this means here is I looked at the graphs of the actual flux of the star versus and the spectra versus the best fit model, which is how these different galactic surveys measure the elemental abundances of stars. And so you can see here where there's a big deviation between the best fit model in red and the actual flux in green, that indicates that there's poor quality data, even though the warning flag was not triggered. And it's because it's right on a calcium absorption line, it would decrease the reliability of the calcium level derived by the best fit model. And so I was only left with one star after all of this filtering out of the original 733,000. And you can see the graph for it here, the spectra graph. And you can see that along the strong calcium absorption line, so these here, it had a very good model match to the actual spectra. Um, and so this star was relatively old. It's around 3/4 the mass of our sun. It's located in the halo. It's not part of a binary system. It's in the red giant phase of its life and has a calcium silicon level of 0.44. And you might not be totally convinced that the star is actually super enriched in calcium compared to other stars around it. But as you can see here on this graph of the galaxy, based on the other stars in the SDSS, they're almost all around have a calcium silicon level around 0.0. But this one is much more has a much greater calcium silicon level all the way up at 0.4 and above. And so I took a look at the more detailed elemental abundances of the star, and you can see it's mostly enriched in calcium and also slightly enriched in oxygen, sulfur, and potassium. And so then but it is mostly enriched in calcium. And as just as a note, actually, this is a log graph. So going up from like 0.0 to 0.1, or going up from 0 to 1, sorry, would be a 10 times increase in the amount of that element. And so based on these elemental abundances, I predicted that the star, or sorry, not just based on the elemental abundances, but because the star was number one enriched in calcium, number two did not have very many heavy alpha elements, and number three was not part of a binary system, I predicted that the star was enriched by a white dwarf binary calcium-rich supernovae. And I think that that finding the star is very interesting because it could really be one of the first steps in learning more about calcium-rich supernovae and the mechanism behind them. And so I'm actually currently in contact with a professor at the University of Notre Dame, Professor Evan Kirby, and he actually helped me get the optical spectra and the visible range for this star. And I'm actually going to meet with him tomorrow to figure out how I should analyze that spectra in order to derive more accurate elemental abundances as well as elemental abundances for more elements, which will really be able help me paint a bigger picture of this star and how it could potentially be calcium enriched. I've also started to expand my search to other databases. So the GALA database, which mostly measures stars in the southern hemisphere, I've started to analyze the elemental abundances for some stars in there. I'm currently figuring out the best ways to determine if a star is actually calcium enriched in that database. And so, yeah, I think that I'm this project's pretty interesting and that it could really be a step forward in understanding the supernova. Thank you.
That's a really cool use of like publicly available data. That's awesome. And how
Yeah.
did you know that you could access all that information?
Well, actually, I learned about this database from actually someone sitting next to me at last year's science fair. I was talking to the guy next to me, and he was explaining his project, and he talked about how he used Sloan's Digital Sky Survey data. And when I was trying to figure out how I wanted to do this project, I just remembered that conversation. I thought, oh, well, it's like he said it was pretty easy accessing all the data, so I might as well just try that. Um, and so yeah, so after I for my actual science fair project, I mostly looked at Sloan Digital Sky Survey data because I had already known that it was easily accessible. But after the science fair was over, I also started expanding my search to other databases.
That's really cool. Thank you, Sam, for giving us
Yeah.
this presentation. Does anybody have any questions or for him?
Let me say something. Yeah, I'm unmuted. I don't know if there are any other judges here. I was the head judge, and I've been that way for 10 or 15 years. The quality of the science fair projects is getting extremely good, and this was a very competitive year. SDAA offers, I think we give almost, in terms of actual cash awards, about a tenth of the value of the awards that are given out. So we're a big player here. And just in case it hasn't been obvious to date, Sam was our number one winner.
Thank you so much for the awards. Yeah. Um, yeah,
No, we're
it
all
was awesome.
impressed.
Yeah. Thank you so much. Yeah. Does anyone have any questions that did I not explain anything fully enough? Or does everyone uh have it
Sounds
well?
like you did pretty good. The chat, I don't see anything in the chat window.
Yeah, I think you
Okay.
did
Sam,
a great
great.
job.
This is Brian. Great job. What do you
Thank
think?
you.
Do you think you're going to do this in college? Do you think you want to stay in astronomy? What's kind of your long term goal for that?
Uh, yeah, I mean, I've I think that before this project, I wasn't super interested in pursuing astronomy in college, but after this project, I really became a lot more interested. I think the sort of problem that I'm having is that I just think almost everything in physics is really cool, and I don't really know like what I want to sort of focus in on, just because there's so much cool stuff going on that it's really hard to just pick one field, in my opinion. Like I think
That's a good
astronomy is
problem
really
to have.
cool. Yeah. Yeah, like astronomy is really cool, like material science is really cool, like theoretical physics is really cool. Like basically there's nothing that seems boring to me, which is a little bit of a problem when it comes to figuring out what I want to focus in on.
You have time to figure it out.
Yeah, it's
So
true.
I did my undergraduate thesis in radiation chemistry, and this is really impressive. You should be really proud.
But thank you.
I do have a question on one of the slides, and I don't know whether you know the answer to this, but in looking at the abundance of the
Yeah.
elements that are produced by alpha capture, it's kind of a sawtooth. Every other element
Yeah.
is lower abundance,
Yes.
and I
Yeah.
just can't I don't know exactly why that would be. Do you
Uh,
know?
yeah, the reason is because the alpha process is like a pretty easy process to happen. Like It's very it's like a pretty common process in supernovae, and it just in like the sort of inside the cores of massive stars in general. But the process, like the reason why it creates even elements is because when a helium nuclei is fused with starting with carbon going up, it only is able to produce even numbered elements because it only has two protons. But the process for creating the odd numbered elements is different and less favorable. And just like it's harder for it to happen in general. And so that's why we see that it's actually it has a name, it's called the odd even effect. Just based on the abundance of the alpha process versus the abundance of processes that lead to odd numbered elements.
You know your stuff. Really good.
Yeah,
Yeah, very impressed.
thank you. Yeah.
That's awesome. Well, thank you, Samuel, for presenting. You clearly deserve this one, and hopefully, good luck on next year's science fair, and
Yeah, thank
hopefully we'll
you.
see you there as well.
Yeah,
Yeah,
thank you so much. Yeah.
yeah. All right. With that, I think Joel, if you're ready, you are up next, my friend. Um, and I'm glad this is being recorded because this laptop is literally about to die. And so I have to actually, I didn't bring my charger. So I'm gonna jump off. But Joel, I will catch this on the recording. I'm excited to hear all about it.
There we go. Back.
There it is.
Don't start sharing your, oh, now where is my presentation?
You are sharing it. Oh, no, not yet.
Yeah. Okay, there we go. Good.
So,
Okay, go ahead.
I was going to say, Francisco needs to stop sharing here.
So is everybody ready? Um, Sam's a tough
Yep.
act to follow. What I'm going to talk about tonight is the Bahtinov mask, actually more generally about focusing and some of the parameters that go into sensitivity to focusing and some things that can go wrong. And this is one of these things where you think you understand it, and then you decide you'll teach it, and you learn some new things. So hopefully, in spite of the fact that we have so many very talented, very experienced people on, that there'll be a little bit for everybody from beginner to expert. And if I do make any mistakes, please feel free to let me know. I'm going to start with just a little fun. I've been tinkering around with my Sea Star, and this is from last night, the North American Nebula from 1 a.m. to 4 a.m. So I guess this morning. Uh, and boy, I'm impressed with this thing. My $6,000 rig definitely produces better images, but I don't know that they're 10 times as good. And that's pretty amazing what you can do, and it's just going to get a lot of people, I think, into the hobby. So kind of some fun there. But I'll talk now about focusing in the Bahtinov mask. It's tough to find any information about the inventor of this thing. It's a Russian guy named Pavel Bahtinov. He is an astrophotographer and inventor, and invented this concept for a mask. There had obviously been other kinds of masks, and will be continue to be new sorts of masks for various purposes in astrophotography and in astronomy in general. But he came up with, I think, a really exceptionally clever idea for helping people focus their telescopes. And of course, you see Bahtinov masks everywhere now. And this guy gave it away. He didn't patent the invention, and we should all be grateful for his contribution to the hobby. So here's a picture of some Bahtinov masks. On the left side, an 8-inch Bahtinov mask for a reflector, a tiny Sea Star Bahtinov mask, and then a tri-Bahtinov mask, which looks really pretty darn complicated. And until you kind of think it through and maybe have look at some diagrams, it is a bit complicated. So what the heck are these things? What do you use them for? And why am I
Hey,
talking?
Joel,
Yeah.
I don't see your shared screen. Unless somebody else does, I don't see it.
I don't
Oh,
see it.
I did click share. Try again.
There you go.
Ah,
There it is.
So
anyway,
just so you know, Joel, we didn't see anything you showed us.
okay. Quickly, there's the image.
There you go. Bing, bing, bing,
okay.
bing.
Okay. Okay. Yeah. Next time, let me know sooner. Okay. So here's a picture of Mr. Bahtinov. And again, just really generous of him to make this invention open source. And here's a few examples of Bahtinov masks. You see them everywhere. Everyone sells them. You can 3D print them. You can cut them out of cardboard. And they're pretty omnipresent. I have them from 8-inch down to my C-Star Bahtinov mask as well. So I want to talk a little bit about what you use these things for, why you might want to use them, and a few factors that come into play in focusing a telescope. So this will be obvious to many of you, but it's worth kind of reviewing quickly. There's a different sensitivity based on the speed of a lens, and photographers really know this because they take advantage of it. Use a wide open lens, an f2.8 lens for portraits to blur out the background, and you use an f8 lens for landscape, as they say, f8 and B there, because you can be pretty sure that everything's going to be in focus. So what's going on there? This is a simple geometric optics diagram that shows parallel rays of light from a star coming into the objective. And this applies to reflector telescopes as well. The light comes in the other direction and bounces back. So all of this will be applicable to reflector telescopes. So a slow telescope has like an f10, like a Schmidt-Cassegrainian telescope, has a very long focal length relative to the size of its aperture, and that makes the focusing cone, the cone of light, very narrow. So within a fairly broad range of distance, you see very little blurring of the image. In other words, focus is relatively easy to achieve and very forgiving. For fast telescopes, simply because the cone of light that is being focused at the center, and I'm just going to talk about the center of the image right now. When you get outside of the center, things get a little bit more complicated, but suffice it to say that it's hard enough to get a good focus in the center. So we're going to talk about that. There's a number of problems with fast telescopes or fast lenses, in that they have this shallow depth of focus, and they're very sensitive to changes in, for example, the geometry of a telescope. And furthermore, when you have this kind of narrow cone like this that narrows down very quickly, they're also very sensitive to tilt. So if the imaging plane itself is tilted or the mirror is tilted, you see a lot of effects on the focus, not only in the center, but on the edges of the field. Let's look at what we see when we go in and out of focus. I'm sure everyone has seen this stuff, these donuts that you see in a telescope. And here is a picture of images of the star being inside of focus on the left here at focus, and outside of focus. It looked pretty much symmetrical. So what you might think of as being a simple cone of light based on geometric optics, and that triangle I showed you in the previous diagram, is a little bit more complicated. You do not see a uniform circle or disk of light. You actually see bands within that disk, and that is due to the wave nature of the light. And we're going to go into that a little bit and talk about some of its repercussions and some of its utility. On the bottom, we have a telescope that is out of collimation, and you can see here, that's easier to see perhaps in this out of focus image, that the dark ring in the center is shifted off to one side, and that's a key indicator that the telescope is out of collimation. And when you get down to focus, you see this coma-like effect, this blurring in one dimension of the star. So the tilt is running in this direction. And I'm going to come back to collimation in a minute. So in thinking about this a little bit, I wanted to really explore what was going on. So I wrote a program to calculate what the cross-section of an image looks like for various telescopes. And I can do this in real time. I can simulate central obstructions, SCTs, different apertures, etc. But I've chosen the example that I heard earlier, a 100 millimeter f10 and a 100 millimeter f5, just to stay the same with the earlier diagram. And the pictures here on the left show you the continuous function of the point spread in focus, and then 1/10 of a millimeter out of focus, so 100 microns, very small amount. And on the right, what that looks like in pixels. So I very conveniently centered the image on a single pixel. If it were in between pixels, it would be kind of divided up and look blocky. And that's what you see in undersampled data. I'm not going to talk about sampling statistics and that, but other than to point out that when you have all your signal or most of your signal in a single pixel, you run the risk of having a very blocky looking image, or you will have a very blocky looking image. Okay, everything looks pretty good for the f10. It looks rather similar at 0.1 millimeter out of focus. Same thing in the actual camera. It's slightly broader, but not, to the eye, perhaps when you're focusing, you're not even going to notice it. At f5, it's a completely different story. First of all, I want to comment here that if you look at this graph, it's narrower. And the only reason it's narrower is because the scale of these images is different. The magnification of an f10 telescope is twice the magnification of an f5 telescope. So the width, the angular width of a pixel is 0.78 arc seconds here and 1.55 arc seconds here. You are actually seeing exactly the same graph, except just at a different scale. But what I wanted to focus on the actual pixels, what you would see in a camera, because it's important, I think, to relate to what we actually observe in a camera when we're doing astrophotography. And if you go 100 microns out of focus, you see a huge effect at this not particularly fast focal ratio. And if you think about it, the f5 is pretty common. It's kind of like a C star. A lot of telescopes, a lot of refractors are at this. If you look at something like a Rasa at f2.2, the effects are really pretty catastrophic for being 100 microns out of focus. Looking at it, you see the similar effect here in the pixels. Again, it's half as wide because you're looking at a much broader field of view, and because all the light is concentrated here, you would have a very undersampled image, and it would look very blocky. Things are different when you go 0.1 micron out of focus. You start to see a donut already. You see the brighter outside and the darker inside of the pixels. Now, what happens if in the real world? So what I've done here is add in seeing and an average 2 arc second seeing. The f10 telescope in focus is broader, and you don't see the little ripples. You don't see the airy disk because of the blurring. And this is going to make it harder to get precise focus. And, that can be important if you're a planetary imager and you're doing lucky imaging and you want to get really precise focus. And that's where we're going to come back to the Bahtinov mask, which will aid you not only visually, but for astrophotography and lucky imaging. You really don't see much when you're a tenth of a millimeter out of focus. Again, same thing here in the actual pixel illumination. Different story at f5. 100 microns out of focus, you see a substantial broadening of the peak. And because of the blurring of the atmosphere, you're going to just see a very broad response across the pixels. This may be my last program that I write by hand, given that Claude and ChatGPT can now write code much faster than I can, like 1,000,000 times faster. But it was a useful exercise to think through the physics. Just a little bit about my background. I'm a physical chemist by training, which allows me to, if somebody asks me about physics, I can say I'm a chemist. And if somebody asks me about physics, I can say I'm a physicist. So get out of being an expert. But at any rate, I wanted to understand the details, and that's why I actually wrote the program with all of the integrations of the wavelets. So let's come back to the diagram for a telescope and the focus cone of light. What if we could encode the light coming in from either side of an objective lens? So I've shown here light coming in on the top. Let's say we put a red filter on it, and on the bottom we put a blue filter. These could be round filters. And when we're inside of focus, the red light is going to be on one side, the blue light is going to be on the other side, their respective sides, retain their respective sides. But when we go past focus, they switch sides. Seems like a good idea, but our eyes are not very sensitive to color. And as we get close to focus, the two colors get right on top of each other and disappear into a dot, making it very, very difficult to see tiny changes around the actual focal point. What we need to do is to somehow distinguish light from one side of the lens from the other side of the lens. We need an encoding method that doesn't shrink to a point, that doesn't focus, that the lens doesn't focus down to a point. So I'm going to review a tiny bit of optics here. First, Huygens principle. So light coming in from a star is a plane wave. The stars are more than 1 light year away, 2 light years away, or billions of light years away. So essentially, the wavefronts are planar. A planar wavefront is mathematically the same as an infinite set of little circular wavefronts. They all add up to give a planar wavefront. On the other hand, a circular wavefront can also be described by a set of individual circular wavefronts, spherical waves. And that's Huygens' principle. The waves don't propagate backwards, but all of the math of wave Fourier optics depends on Huygens' principle, basically integrating all of these little waves to come up with a final solution to show what, like, for example, an image might look like. So let's go back to high school for this. I think it's useful to see the analogies. Physics, you see the same equations in physics and physical chemistry, in mathematics, in just about every possible field, recurring over and over. And this is a high school wave tank. It's got two elements here that are vibrating at the same frequency and in phase. But we could think about this as two slits, light coming in here and propagating out in these spherical wavelets, and light coming in here and propagating out in these spherical wavelets. Well, what happens? In the center, the wavelets add up. But when you go slightly off center, you get destructive interference between the waves. And this is the essence of a diffraction pattern, whether it's a diffraction grating or whether it's a double slit like this, like Young's experiment. So let's take a look a little bit deeper into this. If we have a slit, we have light coming in here, plane waves, and the slit is separated by a distance a, and you look at any particular angle, the difference in distance traveled by the light is just a times the sine of the angle. Okay, it's a really simple equation. And if that distance is equal to an integral number of wavelengths, you get a bright ray coming out. And if it's equal to a half integral number of wavelengths, you get destructive interference and a dark band. What is important to note here is that the slits go into the board here, okay? So where this slit continues on back into the board, into the screen here, you can tell I've been dating myself the board, but the diffraction pattern, the interference occurs perpendicular to the orientation of the slits. So look at that in a little bit more detail. So here we have the mathematical result for a double slit. The waves add up in the center and add up a little bit further out, and then cancel and then add up again. And these are different orders of diffraction. So this is zero order, this is first order, this is second order. When we add a third slit, what happens is everything tightens up. The inner first order diffraction gets brighter, and the higher order diffraction gets smaller. If we go to 5 slits, which is getting pretty close to a Bahtinov mask, we see a very pronounced first order diffraction pattern and a much, much weaker second order diffraction pattern. In the previous slide, I talked about that the constructive interference depends on the number of wavelengths, but that depends on color. And red has a longer wavelength than blue. So the diffraction angle for constructive interference for red is at a higher angle than for blue. So it's spread out. And anytime you have this kind of a slit phenomenon, you're actually doing really spectroscopy. And the place where you see this commonly, sort of the inverse of a slit, is the struts for a secondary mirror. Those produce a diffraction pattern perpendicular to those struts, and you see colors exactly like this. You'll notice that if you have a reflector with a secondary mirror and struts, that you see a very clear color pattern like this. So what does this have to do with focusing? Well, we can use it to do exactly what we wanted to do, and that is to label the light coming in from each side of a lens. So here's the Bahtinov mask, and we have these slits. These slits will produce a diffraction pattern running in this direction, up and down. This is on one side of the lens. On the other side of the lens, we have these angled diffraction patterns. Again, these will produce, diffraction grating. These will produce a diffraction pattern orthogonal to these slits. And if you look at the two of them, they make this nice little X. Okay, and these are spread out. They don't get focused. Why don't they focus? Well, they're coming in at different angles. It's almost like we're creating a field of stars where the light is coming in at different angles and gets focused down to different points on the camera or in your eye if you're doing this visually. So how does that work? This is a really nice diagram from Wikipedia if you spend the time to analyze it. Again, it's an encoding. So think about red light coming in here just for conceptualization. It produces a diffraction pattern perpendicular to the grating. The blue and green light produce diffraction patterns perpendicular to their gratings. When we look at the focus, if we're too near, the red light stays on the same side that it started out on. If we're at focus, the red light is in the middle, and if we're too far from focus, it shifts over to the other side. Actually, both are moving. The X is moving one direction, and the single spike is moving in the opposite direction. And you can see here the results, and I want to point out, you can see very clearly the colors of the diffraction patterns, the first, second, and third order diffraction patterns. And in this image, I've cribbed this image from the web. They've drawn a line through the vertical spike, of diffraction spike. And you can see here that as you achieve focus, you get this really beautiful X-shaped structure with the line in the middle. And as you move out of focus in either direction, they move apart. Now, why is that great? Well, it's good visually because you can pretty much assess when the line is in the middle. And dealing with things like backlash, and I remember in the old days trying to focus things just with my eye and going past focus, and then you got backlash and you're trying to remember exactly how far back to turn. Here, you don't have to mess around with any of that. You can actually see where the focal point is. And furthermore, there are now software packages. I think Nina and some of the other packages actually analyze a Bahtinov mask image and will tell you precisely when you're on focus, which can get you really fine focus for planetary imaging. And this is a really cool simulation of what happens with the Bahtinov mask as you move in and out of focus. It was somebody, Niels Noordhoek, wrote this, and they put it on Wikipedia. And you can see going through focus to the other side of focus, the X will go right across to the other side. And when you're very far out of focus, you just actually start to see what the light would look like just looking through a Bahtinov mask by itself. So here we're tightening everything up. So let's see here. That gives you an idea of why you might want to use a Bahtinov mask. They're really super simple to use. You put it on, slap it on the front of your telescope, you adjust until you get this X pattern, you take it back off, and you're in perfect focus, or about as good as you could ever get. So I showed you that very complicated thing, the tri-Bahtinov mask. And this gets really complicated to kind of figure out. You scratch your head, what am I looking at here? You actually get 3 Bahtinov masks, so one along this axis, one along this axis, and one along this axis. And it's a little bit difficult to figure out what's going on here, so I painted over the different sections in red. This gives you the central spike. This gives you the 2 cross spikes. And same with the blue and the green. The way you use a tri-Bahtinov mask, you use it both for focus and for collimation, because focus is sensitive to the tilt of a mirror. Because if the mirror is tilted, the different sizes of the mirror are not the same distance from the focal point. So here's an example of a system that is slightly out of collimation in the tri-Bahtinov image. The spike here and the spike here are pretty much centered, but you can see this one is off. And this screw needs to be adjusted to bring this into the center point of this X. And then you're going to have perfect collimation without having to wait for a night where you have perfect seeing and can look at the airy disk of a star. So here's some tips for how to use this thing to collimate. The first thing is to cut out some cardboard. So you only have a single Bahtinov mask. This one should be aligned with your collimation screw. And you will get a single Bahtinov diffraction pattern. You can see if it's in focus, and then you can rotate the cardboard to each of the 3 locations to see which one, if any, are out of collimation. So my recipe is I approximately collimate with an out of focus star. So look at the donut, make sure the donut is symmetrical. Use a Bahtinov mask, always remembering to recenter the star, because particularly for reflecting telescopes, Whenever you adjust collimation, you're going to change the position of the star. So you need to recenter it. Replace the Bahtinov mask with a tri-Bahtinov mask aligned to the collimation screws. Zoom in on the diffraction pattern to see if any is off, and then look at one axis at a time and adjust the corresponding collimation screws, repeating, going back and checking. For me, it gets a little frustrating, and I'm going to start using the software. There's Bahtinov Collimator or astrophotography tool, which you can run to actually analyze your image. And I think you can get probably a much tighter collimation using that. And that's all I have. And I'd be happy to entertain questions.
I'll unmute and ask you one. Are these tri-Bahtinov masks with that little masking device, are these commercially available?
I cut out the cardboard myself. That's what people suggest. I think I did see one, and I could do it. I could design a 3D printed one. I 3D print all kinds of stuff. I actually 3D printed the mask itself, but I just thought it would be easier to cut it out of cardboard because you're not cutting slots like you would be for a Bahtinov mask. You're just cutting off a pretty large area. So it's simple. I just traced it out and made it. But I think somebody's got one available, but again, it's got to fit your precise Bahtinov mask, your diameter, and of course the central obstruction. You want a hole for that. So I just figured it was easier to cut out the cardboard.
Joel, it's Brian. How do you use it with the C star? Since it kind of autofocuses itself, how's that?
Yeah, you can do you can do a manual focus. Let's see here. So here's a C star Bahtinov mask, and you just it sort of press fits into the objective, and you can do a manual focus. So I would find a bright star. You don't want things to be too bright and overexposed because it kind of smears out. But a bright star, after you've let the telescope equilibrate to temperature, and then just manually adjust it with the Bahtinov mask. I think some people have had less than perfect success with the autofocusing routine on the C star. I have heard some critiques with that. With my C star, it's been working really pretty darn well. I haven't had to use the Bahtinov mask, but I should have tried it out and taken some pictures for you since I had the C star out last night.
Is there a way to use the Bahtinov mask to deal with back focus tweaking?
Boy, that is a more complicated question. I'm sure that there is a way to use a mask to see improper back focus effects. I don't know what that mask is, and it's not obvious to me that the Bahtinov mask is the right way to do it, because a lot of those I'll just explain back focus. Back focus is usually the distance between the last optical element and the camera sensor surface. And if that's not right, what you can see is a distortion, particularly at the edges of the field of view or away from the center. And of course, with your Bahtinov mask, you're generally focusing the center. You could move the star to the side and look at it, but it's not obvious to me exactly how you would interpret the results. You could maybe focus in this. Oh boy. Yeah, I'm sure there is a mask that could help you with this. There's a lot of creativity to be played with in designing these masks, but I'd have to think about that one some more.
Hey, Joel.
Yeah.
I think on your your $6,000 rig, you use the ASI Air, right? Or do you?
Yeah. Yeah.
So how do you? I mean, you probably compare the autofocusing that you get off of ASI Air combined with their autofocusing with the Bahtinov mask. How does it compare?
I actually haven't compared the two. I get really good results from the ASI autofocuser on the f4 reflector. And I think the reason for that is that the ASI Air, it makes this really nice parabola. It does a statistics of the width of the star, and it accounts for backlash. So it always I think it approaches the final focus from the same direction. And as long as you have, I think, reasonable seeing, what it can do is take that curve and say, I'm going to calculate the minimum of the curve. I don't have to see it. I can calculate it from the total width of the curve. It can estimate pretty darn precisely where the focus is. And I think that's one of the beauties of an autofocuser. I think where the mask can be super useful is for some reason the autofocus isn't working. I think it's super useful for planetary imaging, in particular with something like SharpCap, which does have the analysis of a Bahtinov mask. So if you're really, because for wide field deep sky imaging, you can pixel peep at the stars and maybe see that something is out of focus. But in general, it's not as critical as when you're using lucky imaging. You really, really need to get your focus perfect because you're looking for those moments when seeing is really good and a tiny, tiny bit of out of focus would show up. But I think that the mathematical modeling of the width of the star works really well for most focusers and most telescopes.
Joel, how critical is it to have the center of the Bahtinov mask aligned with the center line of your telescope?
Almost not at all.
Okay, thank you.
Yeah, virtually not at all. It's not, because what you're doing is really encoding the light from one side and the other. And when you're focusing, it doesn't really matter if that's slightly offset, because the preponderance of the light is going to come in from the outside of the mask anyways, because the circumference is bigger. So it should be negligible.
That's good because I hang my Bahtinov mask across the front of my old C8 with a piece of tape, and it's never exactly on.
Yeah, I do. So when I was doing this with my F4 before I got an autofocuser, I had one of these adjustable Bahtinov masks, and I'm sure it wasn't centered dead on. It worked just perfectly.
Okay, thank you.
Sure. Okay.
All right. Sounds like we're Francisco had to bail out because of dead batteries, but if no one else has got anything else to say, we'll close it up for the night. We thank everybody for coming. I'll look forward to some more meetings with some great folks.